Hello, in this session we evaluate the Haber process, the process for the large-scale manufacture of ammonia gas. Ammonia gas is an alkaline gas which dissolves readily in water, forming aqueous ammonia, an alkaline solution that can be used as a water softener. Ammonia gas is also an important smelling salt that is used to reduce fainting, and ammonia gas has a varied range of applications alongside the ones mentioned. To be able to manufacture ammonia gas, we need two raw materials, namely nitrogen gas obtained readily from air by the method of fractional distillation of liquefied air. Secondly, hydrogen gas is obtained naturally from hydrocarbons through the process of cracking. Once the two raw materials, nitrogen and hydrogen, are obtained, a synthesis is introduced in which nitrogen combines with hydrogen readily to form ammonia gas under specialized conditions referred to as the optimum conditions. The optimum condition for the preparation of ammonia gas include temperature, pressure, and catalyst. Number one, the temperature needs to be fixed at 450 degrees Celsius. Under normal circumstances and industrial conditions, it is fixed between 400 to 500, optimum at 450 degrees Celsius. The pressure which is required to convert nitrogen and hydrogen into ammonia gas is an ascending pressure from 200 to 500 atmospheres. And the catalyst required for the process is finely divided iron, normally impregnated by aluminum 3 oxide to boost the yield. Now, let's look at how this happens. To be able to prepare ammonia gas, we have said we need nitrogen gas, which is obtained readily from air by fractional distillation of liquefied air. Secondly, we need hydrogen gas, which is obtained from hydrocarbons by the method of cracking. And thirdly, we have said that to prepare ammonia gas, we synthesize nitrogen with hydrogen in the mole ratio 1:3, and it forms 2 molecules of ammonia gas. The reaction happens to be reversible, and therefore optimum conditions are an essential. An optimum condition is a condition in which the highest yield of the product is formed using the shortest period of time and the least possible effort. These optimum conditions are three. First, the temperature, which runs between 400 to 500 degrees Celsius, is fixed optimally at 450 degrees Celsius, a state in which the reaction is exothermic and forms exclusively ammonia gas. Secondly, the pressure is fixed in an ascending state between 200 to 500 atmospheres. And thirdly, a catalyst is added in the name of finely divided iron. This catalyst speeds up the rate of reaction without itself taking part in the changes in the reaction process. Now, the catalyst enables us to yield roughly 10% of ammonia, or to convert the mixture of nitrogen and hydrogen gas into 10% ammonia gas. Therefore, we may need to impregnate it with aluminum 3 oxide. The aluminum 3 oxide becomes a booster to the catalyst. So this is the catalytic booster. And when we use the catalytic booster in this process, the conversion rate changes from 10% yield into roughly 90% yield. And that would be a suitable condition for rapid preparation of ammonia gas. Next, I would like us to look at the flow diagram. The flow diagram represents the physical process at the industrial domain, how nitrogen and hydrogen are converted into ammonia. As you can see here, there are 5 core chambers in the Haber process. The first chamber is a purifier, the second is a compressor, the third is the yeast exchanger, the fourth is a catalytic chamber, and the fifth is the condenser. To begin with, nitrogen and hydrogen are passed through the refinery in the purifier, where they are removed after they have been cleansed of all impurities, including particulates, dusts, and other particles which are unwanted. Now, once purified, they are taken to the compressor. The compressor is a chamber in which pressure is applied, and the optimum pressure conditions are 200 to 500 atmospheres. So when these gases are compressed, we do not expect them to adhere to one another, but we expect them at least to interact closely. Then, once compression is going on, the compressed gases or the compressed mixture of gases is taken into the heat exchanger, where the temperatures are within the ranges of 400 to 500 degrees Celsius. Within the heat exchanger, there is an interaction or effective reaction between nitrogen and hydrogen gas, which converts them readily into ammonia gas. However, since the reaction is slow, there is a catalytic chamber which is intertwined with the heat exchanger. Within the catalytic chamber, finely divided iron impregnated with aluminum 3 oxide is added, and that process speeds up the rate of reaction such that the ammonia gas formed yields roughly 90% conversion of nitrogen-hydrogen into the required gas. Once this gas has been formed, it is taken to the condenser readily in order to convert it into a liquid product, namely in the sense that ammonia gas is gaseous and therefore will not be easy to contain, and therefore has to be condensed or liquefied to make it easier to contain. And in this respect, we will collect the 90% conversion of ammonia in distinct vats, and the yield will increase continually. Any form of unreacted gases will be referred back to the compressor and recycled in the process, yielding ammonia gas until an optimum condition in which 100% conversion is attained. Now, this is what is referred to as the Haber process. And as we have said, the Haber process is the large-scale manufacture of ammonia gas. And we have said that in the large-scale manufacture of ammonia gas, we need two raw materials, namely nitrogen and hydrogen, which are synthesized at optimum conditions to form the required gas ammonia. We have also said that ammonia gas is an essential gas. One, it can be used as a smelling salt to reduce fainting. It can be used as a water softener when dissolved in water to form aqueous ammonia. And it could also be used in other industrial processes. For example, in the Ostwald process for the large-scale manufacture of nitric acid. Thank you very much. That has been the description of the Haber process.